Aloha and welcome back to chapter 2. So in this video we're going to finish the exercises in this chapter. Let's flip on back and check them out. The last video we covered numbers 3 through 6, so in this one we'll hit exercises 7 through 10. So there they are at the bottom of the page. Let's take a closer look. See, I got my notes here for number 7. Okay, and let's check out all of them. So number 7 deals with the vapor pressure of carbon dioxide, solid carbon dioxide. Number 8, the vapor pressure of a crystal versus that of a liquid. Number 9, the boiling point of liquid iodine. And number 10, carbon dioxide, the molecules. So let's look at number 7. See, we got our helper again, Hershey, hanging out next to her friend Mr. Owl. Okay, number 7. The vapor pressure of solid carbon dioxide, its melting temperature, negative 56.5 degrees, is 5 atmospheres. That's pretty high. The atmospheric pressure is, of course, 1 atmosphere, but at this temperature, carbon dioxide exerts a vapor pressure of 5 atmospheres, so really high. How do you explain the fact that solid carbon dioxide, when used for packing ice cream, doesn't melt to form liquid carbon dioxide? If you wanted to make some liquid carbon dioxide, what would you have to do? So you've probably all seen solid carbon dioxide. That's dry ice. And dry ice is very useful for packing foods because not only is it very cold stuff, but when it warms up, it doesn't really melt. It just evaporates directly into the gas phase. And so why does it do that? That's what this problem is concerned with. Now, the key to answering this and to understanding it is the high vapor pressure of the solid. Solid carbon dioxide, when it reaches its melting point of negative 56.5 Celsius, will have a vapor pressure of 5 atmospheres. So that's really high. Now, you should understand that vapor pressure depends on temperature. And at hotter temperatures, the vapor pressure is higher. So that means at a temperature much lower than 56.5 degrees, the vapor pressure was already 1 atmosphere. Okay, now why does the vapor pressure increase with temperature? Well, think about a chunk of solid carbon dioxide, which is really cold stuff. Now, those solid particles are being held together by the interaction forces between the particles in the solid. Some of the particles along the surface, though, will have more energy than other particles, and those will be the ones that break free from those forces and evaporate. Remember, in any collection of particles, there's always a distribution of energies. Some of them are less energetic and some of them are more energetic. It's kind of like a whole bunch of, molecules vibrating around. Some of them are vibrating more quickly at any given moment, and those will be the ones that have more energy and can break free from the solid. So those will be the ones that vaporize. And vaporization takes place at the surface. Okay, so the solid is in fact evaporating at its surface, even at very cold temperatures. Now, as you increase the temperature of the solid, a larger fraction of those molecules have sufficient energy to escape. And so vaporization takes place more quickly. And so the vapor pressure is higher at higher temperatures. So by the time the temperature reaches negative 56.5, the vapor pressure of the solid is 5 atmospheres. So that means when the temperature is negative 56.5 and the vapor pressure is 5 atmospheres, at some much lower temperature, the vapor pressure would be 1 atmosphere. Okay? Since they increase together, they would decrease together as well. All right? Now, a very cold solid that is warming up already exerts a significant vapor pressure, as we discussed. So, at some temperature well below negative 56.5, the solid's vapor pressure is already matching the surrounding atmospheric pressure of 1 atmosphere. So the solid cannot warm up above this temperature, as it would be vaporizing too quickly. Okay? In fact, the solid can't even warm up above the temperature at which its vapor pressure is 1 atmosphere. It's not even going to be able to reach this temperature. That's actually kind of a typo. The solid's not going to be able to even warm up above the temperature where its vapor pressure matches 1 atmosphere, because it would be vaporizing too quickly as it warmed up. Let's think about how this happens. Suppose you got a very cold solid piece of carbon dioxide, which is at 94 degrees Celsius. Now at 94 degrees Celsius, it's still vaporizing, but only with a pressure of 0.25 atmospheres, and that's lower than the surrounding atmospheric pressure of 1. So the solid will warm up, it will be vaporizing as it warms up, and so by the time it reaches negative 81.0 degrees Celsius, it's still very cold. Now it's evaporating more quickly, and you also have a smaller piece of solid because you lost some along the way. Now its vapor pressure at this temperature is 0.80 atmospheres. But that's still less than the atmospheric pressure. But it's vaporizing more quickly. You see there's a larger concentration of gas particles that are leaving the surface of the solid. And as you warm this up to the point where its vapor pressure actually matches atmospheric pressure, and this occurs at negative 78.5, which is much less than negative 56.5. So at negative 78.5, the vapor pressure of CO2 actually matches atmospheric pressure. Well, now it's not only vaporizing quickly, but it's vaporizing spontaneously. So the carbon dioxide at this point would rather be in the vapor phase rather than the solid phase. Especially if it continues warming up. So you cannot warm up a solid above this. Suppose you tried to. Suppose you tried to put this tiny little piece of carbon dioxide that's left, that's all that's left now, into the oven, and you tried to warm it up to this temperature in order to melt it. Well, if you put it in the oven, the surface of the carbon dioxide would be vaporizing too quickly. You're not going to be able to bring its temperature up to negative 56.5 because it would evaporate too quickly. Now, suppose you took yourself a humongous piece of carbon dioxide and you stuck it in the oven to try to do that. Maybe this is too small of a piece, so let's try a bigger piece. Let's stick that in the oven. Maybe we can, maybe the surface will evaporate, but maybe you can, get at least part of the carbon dioxide up to that temperature. Well, suppose you were able to magically transform, the carbon dioxide and put its temperature at negative 56.5. Well, that means that it wants to form a vapor with a pressure of 5 atmospheres. So if the interior of the solid were at negative 56.5, it would be turning into the vapor phase with a pressure of 5 atmospheres, and that's greater than the surrounding pressure. So this piece of CO2, if it were at this temperature surrounded by 1 atmosphere, it would actually be exploding in all directions with a pressure of 5 atmospheres. It'd be like suppose you had a car tire and you just pop it. What's going to explode? right? Because you're releasing all that pressure. When you have a region that is exerting a pressure of 5 atmospheres, but it's only surrounded by 1 atmosphere, it's just going to explode. And so you're not going to be able to do that. If you try to do it, it would just evaporate along the way. And if you were somehow able to magically, increase the pressure in the middle of this CO2 up to that temperature, then it would just, it would create a bomb, right? It would vaporize like immediately, right? So, kind of hard to do. Now, the second part of the question says, if you wanted to make some liquid carbon dioxide, what would you have to do? Well, you can't do it under a surrounding pressure of 1 atmosphere, but if you were able to put your carbon dioxide in a surrounding pressure above 5 atmospheres, you would actually be able to see it melt. And one way to do it would be to put your CO2 inside of some sort of piston, and you squeeze that piston down so the pressure inside here is above 5. So suppose you do that. Suppose you squeeze it down and now the pressure is 6 atmospheres. Well, now the piece of dry ice will be evaporating and it will actually begin to melt as well. Okay, because the evaporation will continue to take place at the surface, right? Since the surrounding pressure is greater than the vapor pressure of the solid, you see, by the time the solid reaches negative 56.5, it's vaporizing with a pressure of 5 atmospheres, and so vaporization still takes place at the surface, right? And when it reaches 5 atmospheres, some of the solid will actually begin to melt, okay? And the liquid will also be vaporizing. Now you can see this with a phase diagram of CO2 as well. The phase diagram plots the phases of a substance as a function of temperature and pressure. So at different temperatures and pressures, what phases do you have? Now, when the pressure is 1 atmosphere, here, let's zoom in on this. You can see at 1 atmosphere, if you have a piece of solid carbon dioxide, as it warms up, it will convert into the gas phase, and that occurs at a temperature of negative 78.5. Okay, it sublimes directly into the gas phase. In order to have the solid go through the liquid phase and then to the gas phase, the pressure needs to be above 5.11. Okay, so at pressures above this, that's where you'll see the solid melt into the liquid phase and then go into the gas phase. So that's what you have to do. And it's pretty easy to do. You simply put your solid inside of some chamber, or you can squeeze the surrounding pressure, and when you do that, you'll see the solid melt. So, number 8. Define vapor pressure of a crystal, and also vapor pressure of a liquid. Can you think of an argument showing that these two vapor pressures of a substance must be equal at the melting point? Let's first define the two. I usually like to define vapor pressure as follows, and we'll also discuss the textbook definition in a moment. By the way, vapor pressure is discussed on pages 33 through 37. So, the vapor pressure of a crystal is the pressure with which solid particles enter the surrounding vapor phase. So if you have a solid, some of its particles are vaporizing, and therefore they exert a pressure on the surroundings. The pressure with which they're leaving is the vapor pressure. So you can think of it as the solid is sort of pressing out. The gas particles are pushing out. That's the vapor pressure. Okay? Now, pressure is force divided by area, and if you could put a little teeny, area here and you measure the amount of force with which these particles are colliding with that area, then you would be able to measure the vapor pressure. But that'd be really hard to do. There's a better way to go about doing it. You should realize that the vaporization process is a local phenomena, and vapor pressure is occurring right next to the surface of the solid. So if you look at the region above any little part of the solid surface, the concentration of the gas particles up there determines the pressure. The little partial pressure of the gas particles is the vapor pressure. And again, it's the pressure with which they're pushing out. So that's how I define it. Now, how would you actually measure the vapor pressure? Well, that's pretty easy to do, and it's a similar procedure for any substance. So let's just take a look at iodine, for instance. What you can do is put iodine crystals into an evacuated flask and you stopper it. So here you go. Here's an evacuated Erlenmeyer flask, which has solid iodine particles placed in there, and it's been stoppered. And the sidearm is also sealed as well. We'll use the sidearm at the end. So what happens right away is the solid begins vaporizing. The rate of evaporation and condensation, the reverse direction, depends on the temperature and the surface area. So the hotter this is, the faster it's going to be vaporizing, and also the more surface area of iodine that's exposed, it would be also vaporizing more quickly. So if this were pulverized into a powder, it would be vaporizing at a really quick rate. Now, if you wait a little while, now you have a little bit of iodine vapor up there, and some of these gas particles, after colliding with the walls of the container, they might, some of them, lose a little bit of energy and get trapped by the intermolecular forces of the solid. And so you're going to have a little bit of the reverse process occurring. The condensation back onto the solid will be occurring as well. But since there's not as much vapor up here and it's not hitting the surface as often, the reverse rate doesn't match the forward rate. And so it's still vaporizing more quickly than it is condensing. And so the vapor pressure, or the pressure of the gas upstairs, will continue to grow. But eventually it'll reach a concentration up here such that it's condensing as fast as it's vaporizing. And at that point, it's now reached a steady state at which the forward rate equals the reverse rate. And this is now in equilibrium. It's a dynamic equilibrium because stuff is still happening, but it's equilibrium because since the forward and reverse rates are equal, the amount of solid and the amount of gas stay the same. Okay, so the concentration of the gas up in that region, that will not change once this equilibrium is reached. And the textbook on page 33 defines the vapor pressure this way. The gas pressure at this steady state is called the vapor pressure of the crystal. So the way you would measure it would be to hook a gas measuring device up to the flask, and you could use a manometer, which is a U-shaped tube, which is sealed up here and evacuated, and it's filled with mercury. And when you hook this manometer up to the sidearm, then the iodine will flood this region and it'll push the liquid mercury up, and the pressure of the gas then just balances the weight of the liquid, and you can measure the pressure in terms of millimeters of mercury. So that would be how to measure the vapor pressure. Now, the definition of vapor pressure and the method for measuring it that we just discussed also works for liquids. You could also say that the vapor pressure of a liquid is the pressure with which liquid particles enter the vapor phase. So if you have the surface of a liquid, some of the particles will be vaporizing and they're pushing out with a certain pressure. So that's the vapor pressure of the liquid. And also you would measure it the same way. You'd put liquid inside of an evacuated container. You allow it to reach the steady state, and at that point the vaporization equals the condensation rate, and the pressure of the gas upstairs is the vapor pressure of the liquid at that steady state. The second part of problem 8 asks us, can you think of an argument showing that these two vapor pressures of a substance must be equal at the melting point? Well, that's an interesting question, and rather than trying to think up some creative answer, I'm just going to quote the textbook because it answers this problem, or this question. So on page 35, I'll show you here. On page 35, the textbook says, the crystals in the liquid are in equilibrium at the freezing point, melting point. And they then have exactly the same vapor pressure. If the two phases had different vapor pressures, the phase with the larger pressure would continue to evaporate and the vapor would continue to condense as the other phase until the first phase had disappeared. So yeah, see what it's saying? They have to have the same vapor pressure. Suppose they didn't. If one had a larger vapor pressure than the other one at the melting point. So the melting point is when solid is in equilibrium with liquid, right? The solid is in equilibrium with liquid. The substance can't decide whether it's supposed to be a solid or a liquid. They're in equilibrium with each other. Now, if they had different vapor pressures, one of them has a higher vapor pressure, well, it would be wanting to vaporize more quickly than the other one would. Okay, so the one that wants to vaporize more quickly would vaporize more quickly, and the one that doesn't want to vaporize more quickly, well, it would attract those vapor particles. So the one would vaporize, it would disappear, and the other one would increase its mass. And you could picture this. I don't know if it's necessary to picture this, but I went ahead and drew you, a picture of what Pauling is talking about here. Suppose you put solid iodine inside of some evacuated sidearm flask. You cork it, you hook it up to a manometer, and you crank it up low temperature, number 2, and you let it reach 114 degrees Celsius. At that point, the solid has a vapor pressure of 89.7 millimeters of mercury, and also the liquid does too. So that's the melting temperature of iodine. Okay? Now, the solid is in equilibrium with liquid. If you maintain this temperature, you're going to have some solid and you're going to have some liquid. They're in equilibrium with each other. Now, suppose you're maintaining this temperature, the melting temperature, and one of these has a larger vapor pressure than the other one. Well, the one with the larger vapor pressure, which is in equilibrium with its vapor, that's what vapor pressure is, it's the pressure where the solid is in equilibrium with vapor, it would be vaporizing a lot. Okay, and the one with the smaller vapor pressure, if it were the liquid, which is in equilibrium with the vapor, it would be vaporizing a little bit. And since it's in equilibrium, if this one is continuing to produce vapor, this one is continuing to suck it up. And so the solid would disappear and the liquid would gain in mass. Okay, they have to be equal. In order for the solid to be in equilibrium with the liquid, if they're both also in equilibrium with the gas, well, that's how it has to be. For them to be in equilibrium with each other, and they're both in equilibrium with the gas, then they both have to have the same vapor pressure. Let's look at number 9. What is the effect of increase in pressure on the boiling point of a liquid? Estimate the boiling point of liquid iodine at a pressure of 0.5 5 atmosphere. See figure 216. Okay, let's answer the first part. Well, increasing the pressure also increases the boiling point. Now, number 9 is discussed on pages 35 through 37. That's where it talks about boiling. And increasing the pressure of the surroundings also increases the boiling point. You should probably know that. The boiling point is the temperature at which the vapor pressure of the liquid matches the pressure of the surrounding environment. So, boiling occurs when the pressure of the liquid matches the pressure of the environment. So if you increase the pressure of the environment, you have to heat up the liquid even higher to get its vapor pressure to match that. So you see, it's going to be a higher boiling temperature. Now, we can sort of visualize this, maybe. Suppose you have water, for instance. Now, water at room temperature, 25 degrees Celsius, exerts a vapor pressure of 24 millimeters of mercury. Meanwhile, the atmosphere is pushing down with 760 millimeters of mercury. And so vaporization only takes place at the surface, at temperatures below the boiling point. Okay, so at temperatures below the boiling point, vaporization takes place at the surface, and that's because the vapor pressure doesn't yet match the atmospheric pressure. Now, as we heat our water up, when we get to 80 degrees, its vapor pressure is a lot more. Now it's 355 millimeters of mercury, and so it's vaporizing a lot more quickly at the surface, but still it doesn't match 760. And so if you heat it up that extra little bit to 100 degrees, well, now water is vaporizing with a pressure that matches the surrounding pressure. And so water wants to form vapor not just at the surface, but everywhere. So that's why the bubbles form, because water wants to turn from liquid into the gas phase with a pressure that now matches the surrounding pressure. You see, bubbles are not going to form over here. Suppose a little bubble water were to try to vaporize down here in the liquid at this temperature. Well, the atmosphere is going to collapse that bubble before it even forms. The atmosphere is pressing down with more force than the water wants to form the bubble. And so the atmosphere is going to collapse the bubble. But you see over here, now water wants to vaporize with just as much force. And so the atmosphere doesn't have enough force to collapse the bubble. The bubble's going to form. Okay, that's why bubbles form throughout the bulk liquid, because now they're forming with a pressure that matches the surrounding pressure. So the other part of the question says, estimate the boiling point of liquid iodine at a pressure of 0.5 atmosphere. See figure 2-16. So figure 2-16 is right here, and this is the phase diagram of iodine. You see, as a temperature, as a function of temperature and pressure, these are the phases: the solid iodine crystals, the liquid iodine, and the vapor. Okay, now at 1 atmosphere, the transition from liquid to gas occurs right here at 180, looks like about 183 or something, 183 or 184 degrees. So iodine boils at like 184 degrees at 1 atmosphere. But if you decrease the pressure down to 0.5 atmosphere, you can see from the pink dotted line that liquid transitions to the gas at this temperature, which is about 157 degrees. So this part of the curve right here is called the vapor pressure curve, and it tells you at what pressure the liquid is in equilibrium with the gas. Remember, that's what vapor pressure is. It's the pressure where liquid is in equilibrium with gas. Okay, so When the liquid has a pressure of 0.5, the temperature is 157. And so the boiling point at a pressure of 0.5 atmospheres is 157 Celsius. Now, the last problem, number 10, here, let me make a little bit more room up there. Number 10, I have my notes down here. Carbon dioxide, dry ice again, consists of CO2 molecules. These molecules are linear, with the carbon atom in the center. Make 3 drawings representing your concepts of carbon dioxide gas, carbon dioxide liquid, and carbon dioxide crystal, and describe these structures. So, as always, everyone's answer will be a little bit different. I'll give you my take on this. So, number 10, maybe you want to have a look at pages 27 to 35. We're talking about carbon dioxide. This is a linear molecule, and if you draw the Lewis structure, you'll see carbon forms a double bond with one oxygen on one side and another double bond with the other oxygen on the other side. So it's linear. You got the central atom connected by 2 different atoms. Now, in addition to that, these oxygens are also electronegative, and so they suck some of the electron density away from the central carbon. So although this molecule does not have a negative side and a positive side, both of these oxygens are pulling electron density away from the central carbon. Okay, so this is sort of like a long molecule. Maybe the center part is a tiny, has a tiny bit less electron density than the outside ends. So solids, liquids, and gases, here's what I think they would look like. Solids are, of course, very ordered structures. The molecules are all nicely lined up with one another. And since they're flat molecules, linear molecules, I imagine they would probably stack sort of flat against each other. And in addition to that, the center of this molecule, since it has a little bit less electron density, would probably be closely associated with the ends of 2 neighbor molecules, and also these 2 neighbors. So maybe the molecules would be sort of alternating in order for that polar nature of the molecule. Even though it's not polar, the electropositive central carbon might be sitting near to oxygens in the neighboring molecules. So again, solids, they're generally much colder than liquids and gases, and colder means the molecules have less kinetic energy. They're not shaking around as much. You see, the intermolecular forces are strong enough to hold the solid nicely rigid. The molecules are all locked together. Low kinetic energy in the solid. And also, the particles are packed closely together. So solids are kept together by a high pressure. The molecules are close. Molecules have fixed positions, and there is long-range order. You see, the particles nicely line up, and there is long-range order. You could probably say, since the spacing between the carbon dioxide molecules is probably very consistent, you could say with a lot of certainty, what the molecules are doing way far down the line. So a lot of long-range order. Now, if you heat a solid up to a higher temperature, you're giving the molecules more kinetic energy, and so they're shaking around more, and the particles might end up breaking free from those locking interactions and melt into the liquid phase. And now these carbon dioxide molecules would begin to slide past one another. The particles do not have fixed positions now because they have more kinetic energy, and they're able to slide past one another. So liquids are held in place by a medium pressure. So the particles are pretty well closely packed, like a solid. Particles in a liquid are also close together, but maybe there's a little tiny bit more room between some of the particles, okay, versus that of a solid. Again, no fixed positions, and there's also no long-range order. If you look right around any one of the particles, there's probably some short-range order, but you cannot really say with any certainty what any molecules are doing really far away. Okay, there's no long-range order. They're all kind of flowing around past one another. Short-range order, yes, but no long-range order. If you continue to heat up your liquid, you're going to vaporize it completely. The particles will then have enough kinetic energy to completely break free from one another, and then they'll just be flying around independently from each other in the gas phase. So gases are at a high temperature, very high kinetic energy. They're moving very quickly. They're held, in place by a lower pressure. Okay. Molecules are far apart, and of course there is no order in the molecules. They're flying around like a bunch of asteroids out in space or something. So that's my take on that problem, and that closes up chapter 2. Until next time, aloha.